Hello, everyone. My name is King Maina, but you can feel free to call me King. About 3 years ago, I gave a lightning talk titled 5 Things I Wish I Knew Before Moving to Kubernetes. We had just barely started getting familiar with Kubernetes then. A lot of what I mentioned then were more like ideological aha moments rather than problems that we were currently experiencing. And so I figured it would be good to give a talk around the pitfalls of Kubernetes adoption, the actual problems that we've experienced while trying to fully adopt Kubernetes. So who am I? I'm an infrastructure engineer working at a company called Zappi. We're in the business of helping brands make better decisions about ads and innovation that they take to market through consumer testing. I work on the infrastructure team where we manage the company's tech infrastructure and build tooling to support developers. We also closely work with the security team to implement their vision from an infrastructure point of view. I don't work alone. We're 3 on the team, Zach, Hadrian, and I. Together we drive the vision and implement an implementation for our infrastructure. We daily seeking the elusive balance between risk, reliability, risk, and cost. So to set the stage for my talk, we've been running Kubernetes in production for the past 4 years. We are fully on AWS and have self-managed clusters running provisioned by kops. In hindsight, if we were to start migrating now, we'd probably look into managed clusters. It's just that 4 years back, there was no Kubernetes and moving off AWS was not an option. However, we have no regrets. Anything other than kops right now for us introduces many unknown unknowns. We've had success with kops as far as we are concerned. So there isn't any need to fix what's not broken. And we are quite happy. We're quite happy with the idea that all our clusters bootstrapping configuration is all versioned as source code, since kops generates all the state files and Terraform configurations that we need for us to apply as part of our CI run. That said, with that setup and Kubernetes, we're happy that we're now at a place where we have immutable, extensible, scalable, and easily reviewable infrastructure. Our view is that Kubernetes provides an API to some hard problems and an API to a great community. The community is active, welcoming, and has some of the best, the most impressive governance structures that I've ever seen in any open source project. So this talk is not a bash against Kubernetes, nor the community of people and tools around it. We are well aware that the community is continuously working to make things better and easier. The first thing that confronts you when choosing Kubernetes is that a lot of what you're used to do prior no longer applies or has to slightly change. You're confronted with changes in your application as well as your infrastructure, and figuring out what changes are required is very time consuming. And so the first thing you have to do is Dockerize your application. This introduces a steep learning curve for you or your team. If Docker is new technology, you first have to translate package and system level dependencies of your applications as they were managed in your old stack to Docker. This involves choosing the right base image and customizing it as you go along. And that's the easy part. The hard part is realizing that your entire CI/CD pipeline probably needs a revamp to work around issues such as image caching so that you can have a more efficient build and deployment process. How much of this is a problem for you depends on how complex your application is. For example, one of our apps, Docker image, was a whopping 6 GB. This had the adverse effect on image build times on the CI/CD time on the CI/CD side, and deployment times on the CD side. We had to employ some clever tricks in our tooling and scripting to better utilize layer caching in our Docker images. Other hurdles that we had to overcome were how to provide build time secrets, such as SSH keys, to access private repositories and API tokens, to access private package servers. Docker doesn't have a native solution for build time secrets that's easy to work with. And one of the ways I've seen the community around Docker solve this is by trying to use multi-stage builds just to make sure that the secrets aren't layered in. The second step is once you have your Docker image ready, you now have to contend with the finer details when you start to actually run a container of the image. You deal with questions like how do you pass on configuration to your application? How do you pass on secrets? Do you use environment variables or files? What user should your application run as, and what file permissions do they require? An example of something you need to contend with is that you have to factor in that Docker and Kubernetes send sig terms by default. And the question then becomes, is that what your application expects? Should you change the signal using something like stop signals in the Docker image? How does this correlate with what your application requires for graceful termination? In our case, the two applications that we've had to customize signal handling for include Nginx and Rescue. Rescue is a Rails worker process. Both expect sig quits for graceful termination. Other things to consider are where does your application log to? Previously for us, we used to log files to the host. In Docker, we log to standard out, which Docker reads, and then we have agents picking up Docker's logs. You also have to figure out collection of metrics such as resource usage so that you may be able to better profile your application as it runs. And this is particularly important in a Kubernetes context because the resource requests that you set are used by the scheduler to determine the node on which to run the container. The third thing to consider is that once you've ticked all of the boxes from a Docker point of view, you now have to adapt your application to the non-determinism introduced by Kubernetes. For us, we were coming from a legacy stack where we had set node counts, set node types, and predictable scheduling. Over time, our applications had hard-coded assumptions about our infrastructure that posed challenges the moment we tried to run them on Kubernetes. Because now we had to contend with factors such as auto-scaling, pod eviction, and volume AZ binding. Keep in mind, scheduling on Kubernetes is very unpredictable. So you really don't know where your application is running. And it gets even more unpredictable when you factor in other constraints like interpod affinity, node affinity, taints, and tolerations. And as I mentioned before, it's not just your application that will change. You'll have to make changes to your infrastructure too. A highly available and secure Kubernetes cluster likely runs across multiple AZs and has configured multiple public and private subnets. You'll have to think about how to expose your applications. Do you use load balancer per application, or do you use an ingress so that you can have multiple applications, services behind that one load balancer? How does this work with integrating DNS outside the cluster to point to services in the cluster? How do you handle SSL certificates and termination? If you're using a CDN or a WAF, how does that integrate with Kubernetes? Because these are CDNs and WAFs don't have native solutions that work on Kubernetes. The second pitfall is resource planning. Resource planning has never been easy. It's hard, but it's harder in Kubernetes. Kubernetes introduces concepts that make it difficult to predict how much resources your application is going to use at scale. So the first thing is estimating usage. You notice that the scheduler's bin packing approach isn't perfect. Over time, you realize that it's best effort, and ultimately, you will likely end up with a difference between planned usage and actual usage. I'll use 3 extremely simplified examples to illustrate this. First example, you have a 3-core, 3 GB workload on 5-core, 5 GB nodes. And it doesn't matter how much you scale in this case. You'll always waste 2 cores on CPU and 2 GB on memory per node. Second example, if you have workloads with varying ratios of cores and memory requests relative to the node, you could still have wastage if one of the requests utilizes all of what is on the node. Extreme example again, with a 1-core 5 GB node on the same 5-core 5 GB node, you end up with 4 cores wasted. The third example is you find that in Kubernetes, it's common practice to set requests and limits on your nodes, on your workload. This means that an application will be scheduled on a node based on its resource request, and it will be allowed to use up requests up to the resource limits. Since scheduling is based on requests and not limits, it's possible to tightly pack a node such that there isn't room for a workload to exceed its resource request when it needs to. And now when you move outside the pod components, you have to deal with non-pod components. And this is an aspect of Kubernetes that is often overlooked. The resources the non-pod components required to run, such as the operating system components like the SSH daemon, journald. You have Kubernetes system components like kubelet and the container runtime. This is because node resources are categorized into 4. We have kube reserved, which are the reserved resources for Kubernetes system daemons. We have system reserved, which are reserved resources for the operating system components. We have your eviction threshold, which specifies the limit that triggers evictions when node resources drop below the reserved value. We have the allocatable space, which is the remaining node resources that are available for scheduling pods when kube reserved, system reserved, and the eviction threshold resources have been accounted for. And so by default, we find that the entire node capacity is allocatable. The scheduler ensures that for each resource type, the source of the resources scheduled does not surpass the sum of allocatable resources. But suppose you have a couple of applications deployed on the node that is tightly packed, and some of the pods are using up way more than is set on their requests because they are free up to use up more resources up to the limit. This is particularly an issue with non-compressible resources like memory, because even with a eviction threshold of, let's say, memory available set to 100 megabytes, and no cube system reserved or no system reservation set. It's possible for a node to prior to when kubelet is able to reclaim that memory. Then we have the issue around CPU throttling. Even with resource requests and limits set correctly, you could still hit the CPU throttling issue. When memory is exceeded, Kubernetes responds with an but for CPU limit, Kubernetes uses kernel throttling to implement CPU limits. These resources are handled differently because CPU is a compressible resource, while memory is an incompressible resource. So CPU, and you find that now CPU throttling has detrimental effects, especially to latency critical applications. And to make it worse, some kernels have a bug where CPU throttling kicks in before burning through the quota. This bug has been fixed in newer kernels, but you'd have to check. Anyway, there are a couple of solutions around the CPU throttling issue. One, you could increase the limit so that they are not too low, therefore hitting the throttling limit less. Two, I've seen recommendations to remove CPU limits entirely. Three, you could disable the CPU CFS quota enforcement or adjust the CPU CFS quota period to a lower value. Again, you'd have to check whether your Kubernetes version has the flags added because they were added recently. Moving on to costs. Costs going up when using Kubernetes is something you should expect. This is simply because Kubernetes has many moving parts that are all over the place, and it requires some supporting services to support the operator who's managing the cluster. And so if you're running Kubernetes on the cloud, you probably want a production-ready cluster. A production-ready cluster costs. Even before you run any workload, you have to account for the cost of the control plane. The price of the control plane varies based on your distribution. For managed clusters, you have dollar price per hour set for, and for a self-managed cluster, you pay for the resources you use, the node that you spin up, the EBS volumes, and so on. And if you decide to run a higher availability cluster, then you're looking at a minimum of 3 masters so that they can achieve consensus. This also likely means that you'll be operating 3 AZs. So your workload will probably also be split across 3 AZs. In our experience, this has resulted in high data transfer costs since you have a lot of traffic moving across the 3 AZs. You also have to consider the number of clusters you run. Are you running one cluster per application, or are you running a cluster per environment? While you can have each environment in one cluster set to a different namespace, it's not uncommon to separate environments by clusters. In our setup, this is what we've done, as it allows us to completely isolate environments even on the network level. And you can go a step further and even run a cluster for each environment in different AWS accounts. You also find that on each node, you have agents running as daemon sets that take up resources. For example, the logging agent like FluentD, or FileBeat, the metrics agents like Prometheus, Node Exporter. You have security agents for intrusion detection systems or intrusion prevention systems. You have networking agents for the CNIs like Calico, Weave, and Flannel. And other agents like Node Problem Detector and Drano that complement the Kubernetes experience. Each of these don't use much on their own, but they can quickly add up. And so you also have to factor in the hardware that will be required to run the cluster. You'll need NATs for each AZ if you have private subnets. The number of ELBs, which really varies depending on the whether you're spinning up an ELB per service or using an ingress, and even if you choose the ingress route, ingresses have different capabilities. So it doesn't necessarily mean that you'll end up using one. You have to factor in you'll likely use more EBS volume because it's harder to share volume space with deployments and pods. You have to factor in bastions and so on. And as you run all your applications on Kubernetes, you'll probably need a supporting services to make working with your distributed applications more frictionless. You'll probably need a logging stack to aggregate logs quickly and with powerful search of all the components and apps. You'll need a metric stack so that you collect metrics from all the components. This can help you easily anticipate problems and discover bottlenecks. And tracing infrastructure can really help, especially if you're debugging network calls across multiple microservices. As your cluster grows, finding bugs tends to feel like looking for a needle in a haystack, and these supporting services help you make it easier. But the thing is, they cost. For example, if you have a big cluster, you have to apportion a big chunk, a lot of resources to your Prometheus instance and your Elasticsearch instance. And in some cases, you'd want to narrow down spend to a specific service. Kubernetes doesn't provide a native solution. It's hard estimating usage, as I showed earlier, so you can imagine how difficult it is to attribute cost to usage, even if you figured it out. You have to and even if you did figure it out, you have to, based on CPU and memory, you have to consider how do you account for GPUs, how do you account for data transfer costs, shared volumes. You also have to figure out how to account for out of cluster resources such as managed databases, which are typically shared by applications and many applications, and also block storage. And so when you thought it couldn't get any more complicated, you'd have to figure out how to do this while catering for dynamic pricing. If you enable AWS, you probably have a mix of on-demand instances, reserved instances, spot instances, and some instances covered by savings plans. Luckily, there's an open source project that is taking on this challenge. It's worth keeping an eye on. I tried it earlier when it was just new. They claim to do real-time cost allocation based on native Kubernetes concepts. I don't think they've figured it out yet, but at least they're working on it. The other thing to account for is, as an operator, Kubernetes has a steep learning curve, and it's almost impossible to know it all. I'd guess that right now the project is probably millions of lines of code. And this complexity starts with Kubernetes design. It's a system with lots of core components. Everything works great when everything is holding up, but when something goes wrong, you can feel stumped and overwhelmed by all the moving parts. Bear in mind, distributed applications are hard to write correctly and very hard to debug. Kubernetes is not an exception. Layered on top of this architectural complexity is the fact that Kubernetes introduces several new concepts and terminologies. But over and above the core components, you have to manage add-ons that complement the Kubernetes experience. For example, you have auto-scaling add-ons like cluster autoscaler, the vertical pod autoscaler, add-on resizer. You have metrics add-ons like custom metrics adapter, kubestate metrics, metrics server. You have networking and DNS add-ons, external DNS, service meshes, CNIs. You have and other add-ons like ingress controllers, node problem detector, Drano, etcd, and all these kind of provide extra functionality that isn't natively provided by Kubernetes that is very useful. And so you can see the cognitive load of Kubernetes on the operator is very high, just because of the sheer amount of core components and add-ons that you have to maintain and monitor. The last pitfall I want to mention is around tooling. As I mentioned before, our legacy stack was your typical manually provisioned and not so dynamic stack. Moving to Kubernetes posed and continues to pose significant challenges improving our security position. The first thing to realize is that Kubernetes is not secure by default, and it will require work to lock things down. It's my recommendation as to what you can tighten could be, you should enable RBAC, which typically denies everything by default, and you have to explicitly define roles and permissions and the beauty about RBAC is that it allows you to get granular to the resource and action. You should enable encryption at rest. You should enable audit logging, disable public access to the control plane, disable kubelet read-only pod and anonymous authentication unless you need it for some reason. You should disable auto-mounting of the default service account token on service accounts unless the application you're running needs to talk to the API server. You could also do stuff like drop support for insecure TLS cipher suits on kubelet, kube API server, and kube controller. And this is just a few examples of things you could do. I'm sure if you did some more research, you could find more parts to tighten from a security point of view. But in addition to these, we do have some tools that Kubernetes provides that are available at our disposal. We have network policies, which can help us control traffic flow at the IP address and port level. This is particularly helpful because pods are non-isolated in that they accept traffic from any source. Once there's a network policy on a pod, it will reject connections that are not allowed by that network policy. We also have PSPs. These are pod security policies that allow you to define a set of conditions that a pod must run in order to be accepted into the system. So for example, you could enforce that privileged containers and privileged escalation is disallowed. You could prevent use of host path volume mounts and even whitelist allowable volume types. You could even block the sharing of the host process ID, namespace, IPC namespace, and network stack. You could prevent pods that run as root or even prevent the use of certain capabilities. The second thing we had to contend with in regards to security is just how much security tools need to adapt to the new containerized and continuously changing world around Kubernetes. We now have a larger attack surface area with containers, which becomes a challenge for compliance. Kubernetes adds more layers and moving pieces to manage and monitor. We have to worry about the container image, the container runtime, the orchestrator of the containers, and the host upon which orchestration happens. Each pose a set of potential vulnerabilities and risks. You have to worry about providing a layer of isolation between containers, pods, and hosts in an environment that is designed to share resources. Even though larger attack surface area doesn't necessarily mean less security, it does make it harder for the operator to tick off all those security compliance checkboxes. We have network vulnerability scanning. For this type of scanning, you typically introduce a server on a network and allocate a range for it to scan over. The assumption at this point is that most things have simple port exposure that the scanners can pick up. The tools that we used to use in our legacy stack fell apart quite quickly because now we have random ports, thinner nodes, and it's like all the vulnerabilities move from the host to the Docker container, and so we were left with an expensive scanner that we couldn't draw much value on. You have pluggable authentication modules to allow 2FA, gone now, and it's not as easy to identify users who exec into sessions into the containers. In our legacy stack, we used to use a PAM module that allowed us to do 2FA via SSH, and that's gone now with the exec command. Granted, we use webhook authentication that integrates into our in-house provisioning system, but that doesn't account for the fact that once a user is in the container, we don't really have the identity, and this makes it hard to enforce roles and permissions on the application level. We now have confusion on network events due to fixed IP addresses. You find that security tooling is not aware of the difference between the host network and the network overlay provided by the CNI. We've also found that carrying out forensic work is difficult because you have short-lived containers and nodes. So you're left with logs to provide context. And so you tend to turn on all the logs because you don't know when an event will happen that you will need the logs and what in the logs you'll need. We've also noticed that the new intrusion detection systems and intrusion prevention systems and anti-malware systems that work with Kubernetes tend to be very expensive. Pricing is done per node, and more often than not, it will require you a daemon set to run agents on the node. The cost implication here is not only money, but it's also resource utilization. This becomes very expensive at scale. And so what we've done is trying to use open source tools that we could run ourselves and manage, and at least from that point of view, we bear the cost of running it and not having to pay both. And so just to wrap up, Kubernetes is great, but it's likely overkill for small teams and applications. If you're on the Kubernetes adoption journey, I recommend taking containerization as a first step and using a simpler orchestrator like ECS. Probably less featured, but it's okay. You'll consider that moving to Kubernetes will probably need an in-house team. You don't make security an afterthought. Make those decisions early, because some of the configuration that you need is hard to change later on. And if you're choosing Kubernetes, just make sure the benefits outweigh the costs. Every choice you make has pros and cons. And every decision we make at the end of the day is a trade-off. But as SREs, I think we need to remember to keep the main thing the main thing. The goal is just to always balance reliability, risk, and cost for the business. Thanks.